What if I told you that just 40 light-years away from Earth, there's a star system so extraordinary that it has completely rewritten our understanding of planetary systems? A system where 7 Earth-sized worlds orbit so close together that if you stood on one planet, you could see the others looming in the sky like enormous moons. A system where at least 3 planets sit in the habitable zone, where liquid water could exist on their surfaces. A system that might be our best bet for finding life beyond our solar system. This isn't science fiction. This is TRAPPIST-1, and today, we're going to explore every single detail of this remarkable cosmic neighborhood. By the end of this video, you'll understand why astronomers around the world are pointing their most powerful telescopes at this system, and why it might hold the key to answering humanity's oldest question: are we alone in the universe? But before we dive into this incredible journey across 40 light-years of space, I need you to do 3 things. First, if you love space exploration and mind-blowing discoveries about our universe, hit that subscribe button right now. We're building a community of space enthusiasts who want to understand the cosmos, and I don't want you to miss a single video. Second, smash that like button. It helps the YouTube algorithm show this video to more people who are just as fascinated by the universe as you are. And third, drop a comment below telling me which of the 7 TRAPPIST-1 planets you'd want to visit first. I'll be reading every single comment and responding to as many as I can. Now, let's begin our journey to one of the most fascinating star systems ever discovered. The year was 2017. Astronomers held a press conference at NASA headquarters, and what they announced sent shockwaves through the scientific community. They had discovered not 1, not 2, but 7 Earth-sized planets orbiting a single star. And 3 of them were in the habitable zone. The discovery was made using a telescope in Chile called TRAPPIST, which stands for Transiting Planets and Planetesimal Small Telescope. The telescope was specifically designed to search for planets around the smallest and coolest stars in our cosmic neighborhood. And boy, did it deliver. The lead astronomer, Michael Guillon from the University of Liège in Belgium, had been monitoring this particular star since 2015. Initially, the team discovered 3 planets. But as they continued their observations and enlisted the help of NASA's Spitzer Space Telescope, they realized something extraordinary. This wasn't just a system with a few planets. This was a tightly packed system of 7 worlds, all roughly the size of Earth. The announcement made headlines across the globe. Here was a system that looked nothing like our own solar system, yet it contained multiple worlds that could potentially harbor life. The discovery was published in the prestigious journal Nature, and it immediately became one of the most studied planetary systems outside our solar system. But what makes TRAPPIST-1 so special? To understand that, we need to start with the star itself, because this star is unlike anything you might imagine when you think of a sundial. Let's talk about the star at the center of it all. TRAPPIST-1, also catalogued as 2 Mass J23062928-05-02285. This star is what astronomers call an ultra-cool red dwarf, and it's one of the smallest and coolest stars capable of sustaining nuclear fusion in its core. Here's how small we're talking. TRAPPIST-1 has a radius only slightly larger than the planet Jupiter. Let that sink in for a moment. This is a star, burning hydrogen in its core through nuclear fusion, and it's barely bigger than a planet in our own solar system. If you placed it next to our Sun, it would look like a basketball next to a large beach ball. The Sun's radius is about 109 times that of Earth, while TRAPPIST-1's radius is only about 12% of the Sun's radius. The mass of TRAPPIST-1 is approximately 9% of our Sun's mass, or about 84 times the mass of Jupiter. This puts it right at the lower limit for hydrogen fusion. Any smaller, and it would be a brown dwarf, a failed star that never quite got hot enough to start fusing hydrogen. Because of its small size and low mass, TRAPPIST-1 is incredibly cool for a star. Its surface temperature is only about 2,550 Kelvin, or roughly 2,277 degrees Celsius. Compare that to our Sun, which has a surface temperature of about 5,500 Kelvin. This low temperature means that TRAPPIST-1 glows with a deep red color. If you could see it up close, it would look like a giant ember, glowing dully in the cosmic darkness. This coolness has a huge implication. TRAPPIST-1 is incredibly dim. It emits less than 1% of the light that our Sun produces. In fact, it's so faint that despite being relatively close to us in cosmic terms, at just 40 light-years away, you cannot see it with the naked eye from Earth. You would need a decent telescope to spot it in the constellation Aquarius. But here's where it gets really interesting. Because TRAPPIST-1 is so cool and dim, its habitable zone, the region where a planet could have liquid water on its surface, is much closer to the star than it is in our solar system. In our solar system, the habitable zone extends from about 0.95 to 1.37 astronomical units from the Sunday. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. In the TRAPPIST-1 system, the habitable zone is between about 0.011 and 0.021 astronomical units from the star. That's incredibly close. All 7 planets in the TRAPPIST-1 system orbit closer to their star than Mercury orbits our Sunday Mercury. The closest planet to our Sun orbits at about 0.39 astronomical units. The outermost TRAPPIST-1 planet orbits at just 0.063 astronomical units. This tight orbital configuration is possible because the star is so cool. The planets don't get roasted because there's simply not that much heat being emitted. It's like huddling around a campfire versus standing near a bonfire. You can get much closer to a campfire without being burned. TRAPPIST-1 is also an old star. It's estimated to be between 7.6 and 10 billion years old, compared to our Sun's age of about 4.6 billion years. This is great news for the possibility of life. If these planets have been in stable orbits around their star for billions of years, there has been plenty of time for life to emerge and evolve. One more critical fact about TRAPPIST-1. As a red dwarf, it will live for an incredibly long time. While our Sun will die in about 5 billion years, swelling into a red giant and eventually becoming a white dwarf, TRAPPIST-1 will continue burning for trillions of years. Red dwarfs are the misers of the stellar world, burning their hydrogen fuel so slowly that they will outlast almost every other type of star in the universe. However, red dwarfs like TRAPPIST-1 are also known for being temperamental, especially when they're young. They can produce powerful flares, bursts of radiation that could strip away planetary atmospheres. We'll talk more about this challenge when we discuss each planet individually. Now that we understand the star, let's meet its family of 7 planets. The 7 planets of TRAPPIST-1 are designated with letters from B to H, in order of their distance from the star. This is the standard naming convention for exoplanets. The star itself is considered TRAPPIST-1 Ampere, and the planets are TRAPPIST-1b, C, D, E, F, G, and H. All 7 planets are roughly the size of Earth, and most of them have similar densities, suggesting they are rocky worlds like Earth, Venus, and Mars. This is in stark contrast to the gas giants and ice giants of our outer solar system. What makes this system truly unique is how tightly packed these planets are. The entire TRAPPIST-1 system could fit comfortably within the orbit of Mercury. If you stood on one of these planets, the others would appear in the sky much larger than our Moon appears from Earth. During certain alignments, you might see multiple planets at once, creating a spectacular cosmic ballet. The planets are also likely tidally locked to their star, just as our Moon is tidally locked to Earth. This means that one side of each planet always faces the star, experiencing eternal day, while the other side faces away, experiencing eternal night. The region between these two extremes, called the Terminator Zone, might be the most habitable area on these worlds. All 7 planets have orbital periods measured in Earth days, not Earth years. This is because they're so close to their star. The innermost planet, TRAPPIST-1b, whips around its star in just 1.51 Earth days. The outermost planet, TRAPPIST-1 hour, takes about 18.77 Earth days to complete one orbit. Remarkably, the planets appear to be in orbital resonance with each other. This means their orbital periods are related by simple whole number ratios. For example, for every 8 orbits that planet B completes, Planet C completes 5 orbits. These resonances help stabilize the system and are thought to be a clue to how the planets formed. Now, let's explore each planet individually, starting with the innermost world and working our way out. TRAPPIST-1b is the closest planet to the star, orbiting at a distance of just 0.01154 astronomical units, or about 1.73 million kilometers. To put that in perspective, this is less than 5 times the distance from Earth to our Moon. This planet completes one orbit around TRAPPIST-1 in just 1.51 Earth days. Imagine celebrating a birthday every 36 hours. That's how fast this planet moves through its year. TRAPPIST-1b is slightly larger than Earth, with a radius about 1.116 times that of our planet. Its mass is estimated to be about 1.374 times Earth's mass, giving it a density similar to Earth's. This suggests it's a rocky planet with an iron core, similar in composition to Earth. However, TRAPPIST-1b is almost certainly not habitable. Even though its star is cool and dim, the planet orbits so close that it receives about 4 times the amount of radiation that Earth receives from the Sunday. For comparison, Venus, the hottest planet in our solar system, receives about twice the radiation that Earth gets. Scientists estimate that the equilibrium temperature of TRAPPIST-1b, assuming it has no atmosphere, would be around 400 Kelvin, or about 127 degrees Celsius. That's hotter than Death Valley on the hottest day ever recorded. And if the planet has a thick atmosphere with greenhouse gases, like Venus does, the surface temperature could be much higher. The intense radiation from the star means that TRAPPIST-1b has likely lost any water it once had. Any atmosphere it possesses would be under constant assault from stellar radiation. Some models suggest the planet could have a thin atmosphere of heavier molecules, or it might be airless, like Mercury. One intriguing possibility is that TRAPPIST-1b could have a lava surface, at least on the day side. The intense heat could keep rock in a molten state, creating rivers and oceans of lava. If the planet is tidally locked, the night side might be cool enough for rock to solidify, creating a stark contrast between the two hemispheres. Despite its inhospitable conditions, TRAPPIST-1b is scientifically valuable. By studying its atmosphere, or lack thereof, we can learn about atmospheric loss around red dwarf stars. This information is crucial for understanding the habitability of planets in similar systems. Moving outward, we come to TRAPPIST-1c, the second planet from the star. This world orbits at a distance of 0.01581 astronomical units, or about 2.37 million kilometers from TRAPPIST-1. TRAPPIST-1c has an orbital period of 2.42 Earth days. It's slightly larger than TRAPPIST-1b, with a radius about 1.097 times that of Earth. Its mass is estimated to be 1.308 times Earth's mass, giving it a density very similar to Earth's. Like its inner neighbor, TRAPPIST-1c is too hot to be in the habitable zone. It receives about 2.3 times the radiation that Earth receives from the Sunday. This is comparable to what Venus receives, which is why scientists often describe TRAPPIST-1c as a Venus analog. Venus is a hellish world, with a thick atmosphere composed mostly of carbon dioxide, with clouds of sulfuric acid. The greenhouse effect on Venus has run amok, creating surface temperatures hot enough to melt lead, around 462 degrees Celsius. Could TRAPPIST-1c be similar? Early observations of TRAPPIST-1c have been challenging. The planet's small size and the dimness of its star make it difficult to study its atmosphere in detail. However, observations with the James Webb Space Telescope have provided some clues. In 2023, astronomers used JWST to observe TRAPPIST-1c during a secondary eclipse when the planet passes behind the star. By measuring the change in infrared light, they were able to estimate the planet's dayside temperature at about 380 Kelvin or 107 degrees Celsius. This suggests that if the planet has an atmosphere, it's very thin. A thick, Venus-like atmosphere would trap heat more efficiently and create even higher temperatures. The observations also suggest that TRAPPIST-1c probably doesn't have a thick carbon dioxide atmosphere like Venus. If it did, we would expect to see more heat retention. Instead, the planet might have a very thin atmosphere or no atmosphere at all. Why might TRAPPIST-1c lack a thick atmosphere when Venus has one? The answer likely lies in the nature of red dwarf stars. When red dwarfs are young, they're much more active, producing powerful flares and intense ultraviolet radiation. This radiation can strip away planetary atmospheres, especially from planets that orbit as close as TRAPPIST-1c does. Over billions of years, TRAPPIST-1c may have lost its water and much of its atmosphere to space. What remains could be a rocky, barren world, baked by the nearby star. However, there's still much we don't know. Future observations with JWST and other telescopes will help us understand TRAPPIST-1c better. Even if it's not habitable, it serves as a crucial comparison for the other planets in the system. TRAPPIST-1d is where things start to get really interesting. This is the third planet from the star, orbiting at a distance of 0.02228 astronomical units, or about 3.33 million kilometers. The orbital period of TRAPPIST-1d is 4.05 Earth days. This planet is slightly smaller than Earth, with a radius about 0.788 times that of our planet, making it closer in size to Mars. Its mass is estimated to be only about 0.388 times Earth's mass, which gives it a lower density than the inner planets. This lower density is intriguing. It suggests that TRAPPIST-1d might have a significant amount of water, either as ice beneath the surface or possibly as a subsurface ocean. Alternatively, it could have a lower iron content in its core compared to Earth. TRAPPIST-1d sits right at the inner edge of the star's habitable zone. It receives about 1.15 times the radiation that Earth receives from the Sunday. This is more than Earth gets, but it's not necessarily too much for life. If TRAPPIST-1d has a thin atmosphere, the surface temperature could be comfortable, similar to a warm desert on Earth. However, if it has a thick atmosphere with greenhouse gases, the planet could experience a runaway greenhouse effect, making it more like Venus. The equilibrium temperature of TRAPPIST-1d, assuming no atmosphere, is estimated to be around 288 Kelvin, or 15 degrees Celsius. That's actually quite pleasant, similar to Earth's average temperature. But remember, this is without considering atmospheric effects, and it also assumes the heat is evenly distributed across the planet, which is unlikely if the planet is tidally locked. If TRAPPIST-1d is tidally locked, as expected, the day side could be too hot for liquid water, while the night side could be frozen. However, the terminator zone, the boundary between day and night, could have just the right temperature for liquid water to exist. Another possibility is that TRAPPIST-1d has a thick atmosphere that distributes heat from the day side to the night side. This would create more uniform temperatures and potentially make more of the planet habitable. Water is key to TRAPPIST-1d's potential habitability. If the planet formed farther out in the system and migrated inward, it could have accumulated a lot of water ice. As it moved into the habitable zone, this ice would have melted, potentially creating a water world. Scientists are eager to study TRAPPIST-1d's atmosphere, if it has one. Detecting atmospheric gases like oxygen, methane, or carbon dioxide could tell us whether the planet has active geology and possibly even biology. However, we shouldn't get too excited just yet. TRAPPIST-1d's position at the inner edge of the habitable zone means it's vulnerable to atmospheric loss from stellar radiation. If the planet has already lost its water, it could be a dry, rocky world. More observations are needed to determine TRAPPIST-1d's true nature, but it remains one of the most intriguing planets in the system. Now, we come to what many consider the crown jewel of the TRAPPIST-1 system, TRAPPIST-1e. This planet orbits at 0.02928 astronomical units, or about 4.38 million kilometers from the star. TRAPPIST-1e has an orbital period of 6.1 Earth days, It's remarkably similar to Earth in size, with a radius of about 0.92 times Earth's radius. Its mass is estimated to be 0.692 times Earth's mass, giving it a density very close to Earth's. What makes TRAPPIST-1e so special is its position in the habitable zone. It receives about 66% of the radiation that Earth receives from the Sunday. This is actually very close to optimal for habitability. The planet is not too hot and not too cold, sitting comfortably in the middle of the habitable zone. If you could stand on TRAPPIST-1e, and if it has a similar atmosphere to Earth, the temperature would be quite comfortable. The equilibrium temperature, assuming an Earth-like atmosphere, is estimated to be around 246 Kelvin, or about -27 degrees Celsius. But with greenhouse warming from an atmosphere, the surface temperature could be much warmer, potentially similar to Earth's. TRAPPIST-1e is the most Earth-like planet in the system. Its size, mass, density, and position in the habitable zone all suggest it could be a rocky world with the right conditions for liquid water on its surface. If TRAPPIST-1e has retained its atmosphere, it could potentially host oceans. The planet's mass is high enough to maintain a substantial atmosphere against atmospheric loss from stellar winds and flares. And unlike the inner planets, TRAPPIST-1e is far enough from the star that it hasn't been subjected to as much atmospheric stripping. One exciting possibility is that TRAPPIST-1e could be an ocean world, with a global ocean covering its entire surface. If the planet has a thick atmosphere and substantial greenhouse warming, the entire surface could be warm enough for liquid water. Alternatively, if the planet is tidally locked, it could have oceans on the day side, ice on the night side, and a band of liquid water in the terminator zone. This would create diverse environments that could potentially support different forms of life. The planet's density suggests it has a substantial iron core, like Earth. This could generate a magnetic field through a dynamo effect, assuming the planet has a liquid outer core. A magnetic field would be crucial for protecting the atmosphere from stellar wind and maintaining habitability. TRAPPIST-1e is one of the highest priority targets for atmospheric studies with the James Webb Space Telescope and other instruments. Scientists are looking for signs of water, vapor, oxygen, methane, and other gases that could indicate habitability or even life. In 2023, initial JWST observations of TRAPPIST-1e were conducted, though results are still being analyzed. The community is eagerly awaiting more detailed studies that could reveal the planet's atmospheric composition. If TRAPPIST-1e has liquid water and a stable atmosphere, it could be one of the best places in our cosmic neighborhood to search for life. The planet has had billions of years for life to emerge and evolve. If life did develop there, it might be visible through biosignatures in the atmosphere, such as the presence of oxygen and methane together, which would be difficult to explain through geological processes alone. Of all the planets in the TRAPPIST-1 system, TRAPPIST-1e offers the most hope for finding a truly habitable, Earth-like world. It's the planet that keeps astronomers up at night, wondering, could there be life orbiting that dim red star just 40 light-years from Earth? Continuing our journey outward, we arrive at TRAPPIST-1 Farad, the fifth planet from the star. This world orbits at a distance of 0.03853 astronomical units, or about 5.76 million kilometers. TRAPPIST-1 Farad has an orbital period of 9.21 Earth days. It's slightly larger than Earth, with a radius about 1.045 times Earth's radius. Its mass is estimated to be 1.039 times Earth's mass, very similar to our own planet. However, TRAPPIST-1 Farad has a notably lower density than Earth. While Earth has a density of about 5.52 grams per cubic centimeter, TRAPPIST-1 Farad's density is estimated to be around 3.93 grams per cubic centimeter. This lower density is a crucial clue to the planet's composition. The most likely explanation is that TRAPPIST-1 Farad has a significant amount of water. The planet could have a massive subsurface ocean beneath a thick ice crust, or it could be a true water world with a global ocean covering its surface. TRAPPIST-1 Farad sits in the habitable zone, though toward the cooler end. It receives about 38% of the radiation that Earth receives from the Sunday. This is less than Earth, but but potentially enough for liquid water to exist, especially if the planet has a substantial atmosphere with greenhouse gases. Without an atmosphere, TRAPPIST-1 Pharid would be frozen, with an equilibrium temperature around 219 Kelvin, or -54 degrees Celsius. However, if the planet has an atmosphere rich in carbon dioxide or other greenhouse gases, the surface temperature could be much warmer. One fascinating scenario is that TRAPPIST-1 Pharid could resemble Jupiter's moon Europa or Saturn's moon Enceladus. These moons have thick ice crusts covering global subsurface oceans. The ice acts as insulation, keeping the water beneath from freezing solid. Tidal heating from gravitational interactions with other planets could provide additional warmth. If TRAPPIST-1 Pharid is indeed a water world with a subsurface ocean, it could potentially harbor life. On Earth, we've found life in the most extreme environments, including deep beneath the ice in Antarctica and around hydrothermal vents at the bottom of the ocean. Similar environments could exist on TRAPPIST-1 Pharid. The planet's position in the habitable zone makes it less likely to have suffered severe atmospheric loss compared to the inner planets. If TRAPPIST-1 Pharid formed with a substantial volatile inventory, including water and atmospheric gases, it might have retained much of it over billions of years. However, being tidally locked could create challenges for habitability. If the planet has a thin atmosphere, the day side could have liquid water while the night side is frozen. If the atmosphere is thick enough to distribute heat, the entire surface could be habitable. Another possibility is that TRAPPIST-1 Pharid has a thick ice layer on the night side and a liquid ocean on the day side, with a twilight zone of slushy ice and water in between. This would create diverse environments that could potentially support different ecosystems. TRAPPIST-1 Pharid is another high-priority target for atmospheric characterization. Detecting water vapor in its atmosphere would confirm the presence of water and provide clues about the planet's surface conditions. The James Webb Space Telescope and future missions will be crucial for unraveling the mysteries of this potentially ocean-rich world. If we ever send a mission to the TRAPPIST-1 system, TRAPPIST-1 Pharid would be an excellent candidate for exploration. A lander could drill through the ice to reach the ocean beneath, or a submarine could explore the global seas. The discovery of life in such an environment would revolutionize our understanding of biology and the prevalence of life in the universe. TRAPPIST-1 Gram is the sixth planet from the star, orbiting at a distance of 0.04687 astronomical units, or about 7.01 million kilometers. This planet has an orbital period of 12.35 Earth days. It's the largest planet in the system, with a radius about 1.129 times that of Earth. Its mass is estimated to be 1.321 times Earth's mass, giving it a density similar to Earth's. TRAPPIST-1 Gram sits at the outer edge of the habitable zone, and possibly just beyond it. It receives about 26% of the radiation that Earth receives from the Sunday. This is significantly less than Earth, and without a substantial atmosphere, the planet would be frozen. The equilibrium temperature of TRAPPIST-1 Gram, assuming no atmosphere, is estimated to be around 198 Kelvin, or -75 degrees Celsius. That's colder than Antarctica in winter. However, if the planet has a thick atmosphere with strong greenhouse gases, the surface temperature could be much warmer. Some scientists have speculated that TRAPPIST-1 Gram could be similar to Mars, but with more water. Mars is a cold, desert world with a thin atmosphere, but there's evidence of liquid water in Mars's past, and there may be subsurface ice and even briny liquid water today. TRAPPIST-1 Gram could have a thicker atmosphere than Mars, perhaps rich in carbon dioxide or nitrogen. This atmosphere could create enough greenhouse warming to allow liquid water to exist in certain areas, particularly on the day side if the planet is tidally locked. Another scenario is that TRAPPIST-1 Gram is a frozen world with a thick ice shell, similar to TRAPPIST-1 Pharid, but with less internal heating. The planet could have a subsurface ocean kept liquid by tidal heating and residual heat from the planet's formation. The planet's relatively high mass and Earth-like density suggest it has a substantial iron core and rocky mantle. This composition could support geological activity, including volcanism and plate tectonics, which could release gases into the atmosphere and provide energy for life. One intriguing possibility is that TRAPPIST-1 could have geothermal hotspots where liquid water exists despite the generally frozen conditions. On Earth, geothermal areas like Yellowstone support unique ecosystems. Similar oases could exist on TRAPPIST-1. If TRAPPIST-1 has retained significant amounts of water, it could be a frozen water world with a global ice shell potentially hundreds of kilometers thick. Note: beneath this ice, there could be a liquid ocean, warmed by tidal heating and geothermal energy. The presence of a subsurface ocean would make TRAPPIST-1 potentially habitable, at least in the astrobiological sense. Life wouldn't need sunlight if it could obtain energy from chemical reactions, similar to the ecosystems around hydrothermal vents on Earth. Studying TRAPPIST-1's atmosphere will be challenging, but important. Even if the planet is too cold for surface habitability, understanding its atmospheric composition will help us understand how planets at the edge of habitable zones evolve. TRAPPIST-1 represents the transition between habitable and frozen worlds. It's a reminder that habitability is not binary, but exists on a spectrum. Even planets that seem too cold at first glance might have hidden habitable environments beneath their surfaces. Finally, we reach the outermost known planet in the system, TRAPPIST-1. This distant world orbits at about 0.063 astronomical units, or roughly 9.4 million kilometers from the star. TRAPPIST-1 has an orbital period of approximately 18.77 Earth days, the longest in the system. Despite being the farthest planet, it still orbits closer to its star than Mercury does to our Sunday. TRAPPIST-1 is the most mysterious planet in the system. It's smaller than Earth, with a radius estimated to be about 0.755 times Earth's radius, making it similar in size to Mars. However, its mass is difficult to determine accurately due to limited observational data. Based on available measurements, TRAPPIST-1's mass is estimated to be roughly 0.326 times Earth's mass, though this value has significant uncertainty. This gives it a density that could be similar to Mars, suggesting a rocky composition with a smaller iron core compared to Earth. TRAPPIST-1 is almost certainly too cold to be in the traditional habitable zone. It receives only about 13% of the radiation that Earth receives from the Sunday. Without a substantial atmosphere and greenhouse warming, the planet would be a frozen ice ball. The equilibrium temperature, assuming no atmosphere, is estimated to be around 173 Kelvin or -100 degrees Celsius. That's colder than the coldest temperature ever recorded on Earth, which was -89.2 degrees Celsius in Antarctica. However, we shouldn't write off TRAPPIST-1 entirely. If the planet has a very thick atmosphere, possibly dominated by hydrogen, it could trap enough heat to maintain liquid water beneath the ice. This scenario is speculative but not impossible. Another possibility is that TRAPPIST-1 is a frozen water world, similar to Enceladus or Europa in our solar system. These moons have subsurface oceans kept liquid by tidal heating. If TRAPPIST-1 experiences tidal heating from gravitational interactions with the other planets, it could have a subsurface ocean despite the cold surface conditions. The planet's small size and low mass mean it would have difficulty retaining an atmosphere against atmospheric loss, especially given the stellar winds from TRAPPIST-1. However, if it formed with a substantial amount of volatile ices, it could still have a thin atmosphere today. TRAPPIST-1 is the least observed planet in the system, and there's much we still don't know about it. Future observations with JWST and other telescopes will help determine its atmospheric composition, if any, and provide better constraints on its mass and density. One fascinating aspect of TRAPPIST-1 is its potential role in the system's dynamics. The gravitational interactions between all 7 planets create complex orbital resonances. TRAPPIST-1, as the outermost planet, helps anchor these resonances and contributes to the long-term stability of the system. Even if TRAPPIST-1 is too cold for life as we know it, it's scientifically valuable. Studying this planet will help us understand how small planets form and evolve at the outer edges of habitable zones around red dwarf stars. TRAPPIST-1 reminds us that even in systems that seem crowded with potentially habitable worlds, not every planet will be a candidate for life. But each planet, whether habitable or not, teaches us something valuable about planetary science and the diversity of worlds in our galaxy. Now that we've explored each planet individually, let's step back and look at the TRAPPIST-1 system as a whole. This system is not just a collection of 7 planets. It's a finely tuned cosmic machine where every component interacts with the others in fascinating ways. One of the most remarkable features of the TRAPPIST-1 system is the orbital resonance between the planets. Orbital resonance occurs when the orbital periods of planets are related by simple whole number ratios. This creates a gravitational harmony that helps stabilize the system over billions of years. In the TRAPPIST-1 system, near-resonant relationships exist between adjacent planets. For example, for every 8 orbits that planet B completes, planet C completes approximately 5 orbits. This 8-to-5 resonance is one of several that characterize the system. These resonances are thought to have formed during the planet's migration inward toward the star. As the planets moved through the protoplanetary disk early in the system's history, gravitational interactions caused them to lock into these stable configurations. The resonances have important implications for the planet's long-term stability. Without them, the closely spaced planets might have gravitationally perturbed each other, potentially ejecting planets from the system or causing collisions. The resonances act like shock absorbers, maintaining stable orbits over billions of years. Another consequence of the tight orbital configuration is that the planets likely experience significant tidal interactions with each other, not just with the star. These tidal forces can cause tidal heating within the planets, generating internal warmth that could contribute to geological activity and potentially maintain subsurface oceans on the outer planets. The tidal interactions have also likely caused the planets to become tidally locked to the star. Tidal locking means that each planet always shows the same face to the star, just as the Moon always shows the same face to Earth. This creates a permanent day side and a permanent night side. Tidal locking has profound implications for habitability. On the day side, the star would never set, creating a region of perpetual daylight. On the night side, the star would never rise, leaving that hemisphere in eternal darkness. The most temperate regions would likely be in the terminator zone, the boundary between day and night, where temperatures could be moderate enough for liquid water. However, tidal locking isn't necessarily bad for life. If a planet has a thick atmosphere, winds could distribute heat from the day side to the night side, creating more uniform temperatures. This atmospheric circulation could make much larger portions of the planet habitable. The view from any of these planets would be spectacular. Because the planets orbit so close to each other, they would appear enormous in each other's skies. From TRAPPIST-1, for example, the neighboring planets would appear several times larger than our Moon appears from Earth. During certain alignments, you could see multiple planets at once, some showing crescents, others appearing full, creating a celestial display unlike anything we can see from Earth. The planets also regularly transit across the face of the star from each other's perspective. If there were astronomers on TRAPPIST-1, they could study the atmospheres of the other planets by watching them pass in front of the star, just as we study these planets from Earth. The system's compactness also means that communication between planets would be relatively easy, at least compared to interplanetary distances in our solar system. Light takes only a few seconds to travel between planets in the TRAPPIST-1 system compared to minutes or hours in our solar system. If multiple planets harbored intelligent life, they could have near real-time conversations. How did the TRAPPIST-1 system come to be? The current theory is that the planets formed farther out from the star and then migrated inward over time. When stars form, they're surrounded by a disk of gas and dust called a protoplanetary disk. Planets form within this disk as material gradually clumps together. In the TRAPPIST-1 system, the planets likely formed beyond the snow line, the distance from the star where it's cold enough for water to freeze into ice. Beyond the snow line, there's more solid material available for planet formation because water ice is abundant. The planets could have formed as icy worlds, accumulating large amounts of water along with rock and metal. Over time, these planets migrated inward toward the star through a process called disk migration. As planets orbit within the protoplanetary disk, they gravitationally interact with the gas in the disk. These interactions can cause the planets to slowly spiral inward or outward. In the TRAPPIST-1 system, the planets migrated inward, eventually settling into their current orbits. As they migrated, they locked into orbital resonances with each other, which helped preserve the system's architecture. This formation scenario explains why the TRAPPIST-1 planets have relatively low densities compared to Earth. If they formed beyond the snow line and accumulated significant amounts of water ice, they would have higher water content than Earth, leading to lower overall densities. As the planets migrated into the inner system, the water ice on their surfaces would have melted due to the increased stellar radiation. This could have created temporary atmospheres rich in water vapor. However, the intense radiation from the young TRAPPIST-1 star, which was much more active billions of years ago, likely stripped away much of this water vapor, especially from the inner planets. The outer planets, being farther from the star, would have retained more of their water. This is why planets like TRAPPIST-1e, F, and G are considered the best candidates for habitability. They're close enough to receive adequate warmth, but far enough to have retained their volatiles. The TRAPPIST-1 star itself has evolved over its lifetime. When it was young, it was more luminous and more active, producing powerful flares and intense ultraviolet radiation. This early active phase could have eroded the atmospheres of the inner planets, making them less habitable today. However, as TRAPPIST-1 aged, it settled down and became less active. Today, while it still produces flares, they're less frequent and less intense than they were billions of years ago. This means the planets have had a more stable environment for the past several billion years, which is good news for the potential development of life. The TRAPPIST-1 system has been in its current configuration for billions of years, providing ample time for life to emerge and evolve if conditions are right. The orbital resonances ensure the system will remain stable for billions more years, giving life even more time to develop and potentially reach advanced forms. One of the most critical questions about the TRAPPIST-1 planets is whether they have atmospheres. Atmospheres are crucial for habitability. They regulate temperature, protect surfaces from harmful radiation, and can contain the gases necessary for life as we know it. Detecting and characterizing exoplanet atmospheres is one of the greatest challenges in modern astronomy. For planets orbiting distant stars, we can't simply point a telescope at them and take a spectrum like we can with planets in our solar system. Instead, we have to use indirect methods. The primary technique for studying TRAPPIST-1 atmospheres is called transmission spectroscopy. When a planet passes in front of its star from our perspective, an event called a transit, some of the star's light passes through the planet's atmosphere before reaching us. Different gases in the atmosphere absorb light at specific wavelengths, creating a unique spectral fingerprint. By comparing the spectrum of the star during a transit to the spectrum when the planet is not transiting, astronomers can identify which wavelengths have been absorbed by the planet's atmosphere. This tells us which gases are present. The James Webb Space Telescope, launched in December 2021, is revolutionizing our ability to study exoplanet atmospheres. JWST's powerful infrared instruments can detect subtle changes in starlight caused by atmospheric gases, something that was extremely difficult with previous telescopes. The TRAPPIST-1 system has been a high-priority target for JWST since the telescope became operational. In 2023, the first JWST observations of TRAPPIST-1 planets were released, focusing on planets C and E. The results for TRAPPIST-1c suggested that this planet likely does not have a thick, Venus-like atmosphere. The measured dayside temperature was consistent with a bare rock or a planet with a very thin atmosphere. This was somewhat disappointing but not surprising, given the planet's proximity to the star and the likelihood of atmospheric loss. Observations of TRAPPIST-1e are still being analyzed, and the community is eagerly awaiting the results. If TRAPPIST-1e has a substantial atmosphere, it could contain biosignatures, gases that could indicate the presence of life. What biosignatures are astronomers looking for? The most promising include oxygen, ozone, methane, and combinations of gases that would be difficult to explain through non-biological processes. For example, The simultaneous presence of oxygen and methane in an atmosphere is a strong potential biosignature, because these gases react with each other and would quickly disappear unless they're continually replenished by biological or geological processes. However, detecting biosignatures is extremely challenging. Even with JWST, we need multiple observations over several years to build up enough data to confidently identify atmospheric gases. The TRAPPIST-1 star is very dim, which means we're working with very little light, and extracting tiny signals from this faint light requires extraordinary precision. Another challenge is distinguishing between biological and non-biological sources of gases. For example, oxygen can be produced by photosynthesis, but it can also be produced by the photodissociation of water molecules followed by the escape of hydrogen to space. Methane can be produced by microbes, but it can also be produced by volcanic activity or chemical reactions in hydrothermal systems. To confidently identify biosignatures, astronomers need to detect multiple gases and understand the planet's overall atmospheric chemistry, surface conditions, and geological activity. This requires many hours of telescope time and sophisticated modeling. Beyond JWST, future telescopes will continue the search for atmospheres and biosignatures in the TRAPPIST-1 system. NASA's Habitable Worlds Observatory, planned for the 2042, and ESA's Plato mission will provide additional capabilities for studying these planets. The search for atmospheres in the TRAPPIST-1 system is one of the most exciting frontiers in astronomy. Within the next decade, we may know whether these planets have atmospheres, whether they contain water vapor, and whether there are any hints of life. The answers could transform our understanding of our place in the universe. While the TRAPPIST-1 system offers exciting possibilities for habitability, it also presents significant challenges. Understanding these challenges is crucial for assessing the true potential for life in this system. The first major challenge is stellar activity. Red dwarf stars like TRAPPIST-1 are known for producing powerful flares, especially when they're young. A stellar flare is a sudden, intense burst of radiation caused by magnetic field interactions on the star's surface. These flares can be thousands of times more energetic than the largest flares from our Sun. When a flare occurs, it bathes nearby planets in intense ultraviolet and X-ray radiation. This radiation can strip away atmospheric molecules, gradually eroding the atmosphere over millions or billions of years. For the inner TRAPPIST-1 planets, atmospheric loss due to stellar activity is a serious concern. Computer models suggest that planets B and C have likely lost substantial amounts of their original atmospheres. Even planets D and E may have experienced significant atmospheric erosion, though they're farther from the star and may have retained more of their volatiles. However, there's hope. If the TRAPPIST-1 planets have active geology, including volcanism, they could continually replenish their atmospheres by releasing gases from the interior. Earth's atmosphere has been maintained partly through volcanic outgassing over billions of years. Similar processes could occur on the TRAPPIST-1 planets. The second challenge is tidal locking. As we discussed earlier, the TRAPPIST-1 planets are likely tidally locked, with one side always facing the star. This creates extreme temperature differences between the day and night sides. On planets with thin atmospheres, the day side could be too hot for liquid water, while the night side could be frozen solid. Liquid water might only exist in a narrow band at the terminator zone, the boundary between day and night. However, if a planet has a thick atmosphere, winds could redistribute heat from the day side to the night side. Climate models suggest that even a relatively thin atmosphere could be sufficient to prevent the night side from freezing completely, expanding the potentially habitable regions. A third challenge is the lack of a strong magnetic field. Earth's magnetic field, generated by the motion of liquid iron in our planet's outer core, protects our atmosphere from the solar wind. Without this magnetic shield, the solar wind would gradually strip away our atmosphere. We don't know whether the TRAPPIST-1 planets have magnetic fields. Generating a magnetic field requires a liquid, electrically conductive outer core and sufficient heat to drive convection. The TRAPPIST-1 planets' masses and densities suggest they could have iron cores, but whether these cores are liquid and convecting is unknown. If the TRAPPIST-1 planets lack magnetic fields, their atmospheres would be more vulnerable to erosion by stellar wind. However, a thick atmosphere can partially shield itself through its own interaction with the stellar wind, so a magnetic field might not be absolutely necessary for maintaining an atmosphere over billions of years. A fourth challenge is the composition of the planets. If the TRAPPIST-1 planets formed beyond the snow line and migrated inward, they could have very different compositions than Earth. They might be richer in water and lighter elements, with smaller iron cores. If the outer planets are true water worlds with deep global oceans and no exposed land, this could actually pose a problem for life. On Earth, many critical elements for life, like phosphorus, are concentrated in rocks on land. Rain and rivers transport these nutrients to the oceans, where they support marine ecosystems. Without a rock-water cycle involving land and ocean, it's unclear whether water worlds could support abundant life. However, even on a water world, hydrothermal vents on the ocean floor could provide the energy and nutrients necessary for life. On Earth, hydrothermal vent ecosystems are among the most productive in the deep ocean, supporting unique organisms that don't rely on sunlight. Finally, there's the challenge of confirming habitability from 40 light-years away. Even if one or more TRAPPIST-1 planets are habitable, and even if they harbor life, detecting that life from Earth is extremely difficult. We need to accumulate many observations, build detailed atmospheric models, and rule out non-biological explanations for any potential biosignatures. Despite these challenges, the TRAPPIST-1 system remains one of the most promising places to search for life beyond Earth. The challenges are significant, but they're not insurmountable. With continued observations and advances in technology, we're steadily moving closer to answering whether these worlds are habitable. To truly appreciate how unusual the TRAPPIST-1 system is, it's helpful to compare it to our own solar system. The differences are striking and reveal just how diverse planetary systems can be. First, let's talk about system architecture. Our solar system is spread out over vast distances. The inner rocky planets Mercury, Venus, Earth, and Mars are relatively close to the Sun, but there are still large gaps between them. Then there's a huge gap before we reach the gas giants, Jupiter, Saturn, Uranus, and Neptune. The TRAPPIST-1 system, in contrast, is incredibly compact. All 7 planets orbit closer to their star than Mercury orbits our Sunday. If you placed the entire TRAPPIST-1 system in our solar system, it would fit comfortably within Mercury's orbit with room to spare. The compactness of TRAPPIST-1 creates a very different environment. In our solar system, the planets are largely independent of each other. Gravitational interactions between planets exist, but are relatively weak. In TRAPPIST-1, the planets are so close that they significantly influence each other's orbits and dynamics. Second, the star itself is vastly different. Our Sun is a G-type main-sequence star, medium-sized and yellow in color. TRAPPIST-1 is an M-type ultra-cool dwarf, tiny and red. The Sun is about 8 times larger than TRAPPIST-1 radius and over 11 times more massive. The Sun is also much hotter and brighter than TRAPPIST-1. The Sun's surface temperature is about 5,500 degrees Celsius, while TRAPPIST-1's is only about 2,277 degrees Celsius. The Sun emits about 100 times more energy than TRAPPIST-1. These differences have profound implications for the planets. Because TRAPPIST-1 is so dim, its habitable zone is much closer to the star than ours. This close proximity leads to tidal locking, which doesn't occur for Earth because we're farther from the Sunday. Third, the timescales are different. Our Sun formed about 4.6 billion years ago and has a total lifespan of about 10 billion years. It's currently in the middle of its life. TRAPPIST-1, on the other hand, is between 7.6 and 10 billion years old, already older than our Sun, and it will continue burning for trillions of years. This longevity is actually good news for life. If life took billions of years to develop intelligence on Earth, planets in the TRAPPIST-1 system have even more time. However, the early, active phase of TRAPPIST-1, when it was producing intense flares, may have made it difficult for life to get started. Fourth, there's the question of planetary diversity. Our solar system has tremendous diversity. rocky inner planets, gas giants, ice giants, numerous moons, asteroids, comets, and a distant icy region called the Kuiper Belt. The TRAPPIST-1 system, as far as we know, consists only of 7 rocky planets relatively similar in size. There don't appear to be any gas giants in the system. This lack of gas giants might actually be an advantage for the TRAPPIST-1 planets. In our solar system, Jupiter acts as both a protector and a threat. Its powerful gravity deflects many comets and asteroids away from the inner solar system, reducing the number of impacts on Earth. But Jupiter can also gravitationally perturb objects and send them toward the inner planets. Without a Jupiter-like planet, the TRAPPIST-1 planets might experience fewer catastrophic impacts, which could be beneficial for the long-term stability of life. However, they might also receive fewer deliveries of water and organic compounds from comets, which could have helped seed life on Earth. Fifth, the habitability potential differs dramatically. In our solar system, only one planet Earth is clearly habitable on its surface. Mars might have been habitable in the past, and some moons like Europa and Enceladus might have subsurface oceans, but Earth is the only world we know of with abundant surface liquid water and life. In the TRAPPIST-1 system, there are potentially 3 or 4 planets in or near the habitable zone, TRAPPIST-1d, E, F, and possibly G. This dramatically increases the chances that at least one of these worlds is habitable. If the odds of a single habitable zone planet actually being habitable are, say, 10%, then having 4 such planets in one system increases the overall probability that at least one is habitable. Finally, there's the matter of observation. We can study planets in our solar system in exquisite detail using spacecraft. We've landed rovers on Mars, sent probes into Jupiter's atmosphere, and flown past Pluto. We can see surface features, analyze soil and rock samples, and measure atmospheric composition with precision. For TRAPPIST-1, we're limited to observations from 40 light-years away. We can't see surface features or send spacecraft there, at least not with current technology. We're limited to indirect observations, measuring the tiny dips in starlight when planets transit, analyzing the subtle changes in that light to infer atmospheric composition, and using computer models to understand what these worlds might be like. Despite these limitations, the TRAPPIST-1 system offers something our solar system doesn't: multiple potentially habitable Earth-sized worlds in a single system. This makes it an extraordinary target for the search for life beyond Earth. The study of the TRAPPIST-1 system is still in its early stages. We've known about this system for less than a decade, and we're only beginning to unlock its secrets. But the future of TRAPPIST-1 research is incredibly exciting, with new observations and missions on the horizon. The James Webb Space Telescope is currently leading the charge in studying TRAPPIST-1. JWST's powerful infrared capabilities allow it to detect the faint signatures of atmospheric gases in exoplanet atmospheres. Over the next several years, JWST will conduct many more observations of the TRAPPIST-1 planets, building up detailed atmospheric profiles. These observations will focus on detecting key molecules like water vapor, carbon dioxide, methane, oxygen, and ozone. The presence and abundance of these gases will tell us whether the planets have substantial atmospheres, whether they contain water, and whether there are any hints of biological activity. JWST can also measure the temperatures of the planets more precisely, helping us understand their climates. For tidally locked planets, JWST can measure the temperature difference between the day and night sides, which reveals how well the atmosphere distributes heat. Beyond JWST, several other current and future missions will contribute to our understanding of TRAPPIST-1. NASA's upcoming Nancy Grace Roman Space Telescope, set to launch in the mid-2022, will primarily focus on dark energy and exoplanets around more sun-like stars, but it could potentially make observations of TRAPPIST-1 as well. ESA's Plato mission, scheduled for launch in 2026, will search for Earth-sized planets in the habitable zones of sun-like stars. While TRAPPIST-1 isn't its primary target, Plato's high-precision photometry could provide additional data on the TRAPPIST-1 planet's transits, helping refine our knowledge of their sizes and orbits. Looking further ahead, NASA is developing the Habitable Worlds Observatory, a next-generation space telescope specifically designed to search for signs of life on exoplanets. This mission, planned for the 2040 seconds, will have the capability to directly image some exoplanets and analyze their atmospheres in unprecedented detail. TRAPPIST-1 could be a prime target for this mission. There's also the possibility of ground-based observations. The extremely large telescope, currently under construction in Chile, will be the largest optical telescope in the world when completed. With a primary mirror 39 meters in diameter, it will have unprecedented light-collecting power and could potentially study the atmospheres of the TRAPPIST-1 planets. Beyond observations, theoretical work on the TRAPPIST-1 system continues to advance. Scientists are developing increasingly sophisticated climate models to understand what these planets might be like. They're modeling how tidal locking affects climate, how atmospheres distribute heat, and how magnetic fields, or the lack thereof, influence atmospheric retention. Astrobiologists are also thinking about what kinds of life might exist on the TRAPPIST-1 planets. If these worlds are habitable, would life there resemble life on Earth, or would it be fundamentally different? How would organisms adapt to a tidally locked world with a dim red sun? These questions are driving new research into extremophile organisms on Earth and the fundamental requirements for life. There's even early discussion about sending a mission to TRAPPIST-1, though this is far in the future and faces enormous technological challenges. At 40 light-years away, TRAPPIST-1 is relatively close in cosmic terms, but with current technology, it would take tens of thousands of years to reach. However, concepts for interstellar probes, such as breakthrough initiatives like Breakthrough Starshot, which proposes using powerful lasers to accelerate tiny spacecraft to a fraction of the speed of light, could potentially reach TRAPPIST-1 in a century or two. Such a mission would require revolutionary advances in propulsion, miniaturization, and power generation. But if we could send even a small probe to TRAPPIST-1, it could return images and data that would be impossible to obtain from Earth, perhaps even confirming the presence of life. In the nearer term, the focus will remain on remote observations. Every new piece of data brings us closer to understanding whether the TRAPPIST-1 planets are habitable and whether they might harbor life. The next decade will be particularly crucial as JWST and other telescopes accumulate enough data to draw firm conclusions about these worlds. The discovery and study of the TRAPPIST-1 system have implications that extend far beyond this single star system. This discovery has fundamentally changed how we think about planetary systems, habitable zones, and the search for life in the universe. First, TRAPPIST-1 has shown us that planetary systems can be very different from our own solar system and still potentially harbor habitable worlds. Before TRAPPIST-1, most of our ideas about habitability were based on our solar system. We thought of Earth as the model for habitability, orbiting a sun-like star at a comfortable distance. TRAPPIST-1 has expanded our concept of where life might exist. Habitable planets don't need to orbit sun-like stars. They can orbit cool red dwarfs, which are the most common type of star in the galaxy. This dramatically increases the number of potentially habitable worlds in the universe. Red dwarfs make up about 75% of all stars in the Milky Way galaxy. If even a small fraction of red dwarfs have habitable planets like those in TRAPPIST-1, then there could be billions of habitable worlds in our galaxy alone. This is a staggering implication for the search for extraterrestrial life. Second, TRAPPIST-1 has demonstrated that small, cool stars can host multiple planets in their habitable zones simultaneously. This challenges the idea that habitable zones are rare. Instead, it suggests that nature might be quite good at producing potentially habitable worlds, at least in terms of placing planets at the right distance from their stars. However, TRAPPIST-1 has also highlighted the challenges of habitability around red dwarfs. The stellar activity, tidal locking, and potential for atmospheric loss mean that not every planet in a habitable zone will necessarily be habitable. Determining which factors are most important for true habitability remains an active area of research. Third, the discovery has energized the field of exoplanet research. Since the first exoplanet orbiting a sun-like star was confirmed in 1995, astronomers have discovered thousands of exoplanets. But TRAPPIST-1 stands out as one of the most exciting systems because of its multiple, potentially habitable worlds and its relative proximity to Earth. The attention TRAPPIST-1 has received has led to increased funding and interest in exoplanet research. New telescopes and instruments are being developed specifically to study systems like TRAPPIST-1. The search for life beyond Earth is no longer purely theoretical. It's an active observational science with concrete targets. Fourth, TRAPPIST-1 has inspired public interest in astronomy and space exploration. The announcement of the 7 planets captivated people around the world. It sparked imaginations and reminded us that there are incredible discoveries yet to be made about our universe. This public interest is crucial for sustaining support for space science. When people are excited about discoveries like TRAPPIST-1, they're more likely to support funding for space telescopes, planetary missions, and basic research into astrobiology and planetary science. Fifth, TRAPPIST-1 has raised profound philosophical questions. If we discover that one or more of the TRAPPIST-1 planets harbor life, it would be one of the most significant discoveries in human history. It would confirm that life is not unique to Earth and that the universe might be teeming with living worlds. Even if we don't find life on TRAPPIST-1, the system teaches us about the diversity of planetary environments and the factors that make a world habitable. This knowledge feeds back into our understanding of Earth's uniqueness, or lack thereof, and our place in the cosmos. The TRAPPIST-1 system represents a new era in astronomy, the era of comparative planetology across interstellar distances. We're no longer limited to studying planets in our own solar system. We can now study entire planetary systems around other stars, comparing them to our own, and learning about the full range of planetary possibilities. As our technology improves and our understanding deepens, we'll be able to answer questions that seemed impossible just a few decades ago. Are we alone? Is Earth special? What does it take for a planet to be habitable? TRAPPIST-1 is bringing us closer to answering these ancient questions. Let's engage in some informed speculation about what life might be like on the TRAPPIST-1 planets if it exists. While this is necessarily speculative, we can make educated guesses based on what we know about life on Earth and the conditions on these distant worlds. First, consider the light environment. The TRAPPIST-1 star emits most of its energy in the infrared, with a deep red color visible to human eyes. Any photosynthetic organisms on the TRAPPIST-1 planets would need to adapt to this light environment. On Earth, plants appear green because they reflect green light and absorb red and blue light for photosynthesis. On a TRAPPIST-1 planet, plants might appear black or very dark to maximize absorption of the limited visible light. They would be specifically adapted to capture infrared light, which is abundant from the red dwarf star. Some scientists have suggested that photosynthetic organisms on red dwarf planets might use different pigments than chlorophyll, perhaps absorbing light across a broader spectrum to maximize energy capture. The landscapes might look alien to our eyes, with dark vegetation covering the habitable regions. If a TRAPPIST-1 planet is tidally locked, life would have to adapt to the permanent day-night division. On the day side, organisms would need protection from constant radiation exposure. They might live underground, under rocks, or develop thick protective layers. Alternatively, they might be active only during times when stellar flares are less likely, though predicting flares is difficult. On the night side, any life would need to survive without direct sunlight. However, this doesn't mean life is impossible. On Earth, we have entire ecosystems around hydrothermal vents on the ocean floor that don't depend on sunlight at all. These ecosystems run on chemosynthesis, deriving energy from chemical reactions rather than photosynthesis. Similar ecosystems could exist on the night side of a tidally locked TRAPPIST-1 planet. The terminator zone, between day and night, might be the most hospitable for life. Here, the temperature would be moderate, and organisms could potentially move between the day and night sides as needed. Flying creatures could migrate daily, while plant-like organisms might root themselves in the twilight zone where conditions are stable. If the planet has a thick atmosphere with strong winds, the entire planet might have a more uniform temperature, making more of the surface habitable. In this case, life could potentially exist across the day and night sides, with different species adapted to different light and temperature conditions. Water would be crucial for life on TRAPPIST-1 planets, just as it is on Earth. If liquid water exists, whether on the surface or underground, It could support life. Even on planets that seem too cold on average, like TRAPPIST-1 Farad or G, subsurface oceans could harbor life similar to what might exist in Europa's ocean. If intelligent life were to evolve on a TRAPPIST-1 planet, their perception of the universe would be very different from ours. They would grow up seeing their neighboring planets looming large in the sky, obviously, other worlds. The concept of other planets would be intuitive to them, unlike humans who only realize the planets in our sky were other worlds relatively recently in our history. They might develop astronomy earlier than we did, with a clear understanding of orbital mechanics from observing their sister planets. Interplanetary travel might seem more achievable to them since the other planets would appear so close in the sky. However, their view of the wider universe would be limited by their dim star. The TRAPPIST-1 star is so faint that it would be difficult to see distant stars during the day. The sky might appear darker than Earth's daytime sky, with stars visible even when the sun is up. This could give TRAPPIST-1 inhabitants a constant connection to the wider cosmos. The possibility of life on multiple planets in the same system is tantalizing. If TRAPPIST-1, E, F, and G all turned out to be habitable, could life exist on all three? Could life transfer between planets on meteorites ejected by asteroid impacts, a process called panspermia? If so, life on the three planets might share a common origin and have similar biochemistry. It's even possible to imagine, far in the future, a scenario where intelligent life on one TRAPPIST-1 planet makes contact with intelligent life on another planet in the same system. The close proximity would make interplanetary communication and travel far easier than in our solar system. Of course, all of this is speculation. We don't yet know if any TRAPPIST-1 planet is habitable, let alone inhabited. But the possibilities are fascinating to contemplate and drive our desire to learn more about this extraordinary system. We've taken an incredible journey through the TRAPPIST-1 system, exploring 7 remarkable worlds orbiting a dim red star 40 light-years from Earth. We've learned about the tiny, ancient star at the system's heart, the tightly packed orbits of the planets, and the potential for multiple habitable worlds in a single system. TRAPPIST-1 represents one of humanity's best opportunities to answer the age-old question: are we alone in the universe? Within our lifetime, we might discover definitive evidence of life on one of these planets, or we might find that they're all barren. Either answer would be profound. If we find life, it would fundamentally change our understanding of our place in the cosmos. We would know that life is not unique to Earth, that the universe is likely filled with living worlds. It would raise new questions about the nature of life, its origins, and whether intelligent life might be common or rare. If we find that the TRAPPIST-1 planets are lifeless, despite being in the habitable zone, that would also teach us something important. It would help us understand the factors that make a planet truly habitable, beyond just being at the right distance from its star. It would inform our search for life elsewhere and help us appreciate how special Earth might be. The search for life on TRAPPIST-1 is just beginning. Over the next decade, as the James Webb Space Telescope and other instruments accumulate observations, we'll learn whether these planets have atmospheres, whether they contain water, and whether there are any signs of biological activity. This is science in action, the process of discovery unfolding in real time. We're fortunate to live in an era when we can study other planetary systems in such detail, when we can search for signs of life on worlds orbiting distant stars. The TRAPPIST-1 system reminds us of the incredible diversity of the universe and the countless worlds that exist beyond our own. It challenges our assumptions about what a planetary system should look like and where life might exist. It expands our cosmic perspective and our sense of possibility. As we continue to study TRAPPIST-1 and other exoplanet systems, we're not just learning about distant worlds. We're also learning about ourselves, about Earth, and about the remarkable cosmic journey that led to our existence. We're part of a universe that creates stars and planets, that might create life in countless places, that continues to surprise and amaze us with its complexity and beauty. The story of TRAPPIST-1 is still being written. Each new observation adds a chapter, bringing us closer to understanding these distant worlds. Whether we ultimately find life there or not, the journey of discovery is itself worthwhile, expanding human knowledge and inspiring us to keep exploring. 40 light-years away, 7 worlds orbit a dim red star. They've been there for billions of years, and they'll remain for billions more. Now, for the first time in cosmic history, another form of intelligence from a planet orbiting a different star is studying them, wondering about them, dreaming about them. That connection across 40 light-years of space, that reaching out to understand other worlds, is one of the noblest endeavors of our species. It's what makes us explorers, scientists, dreamers. And the TRAPPIST-1 system, with its 7 Earth-sized worlds, is calling us to explore, to discover, to understand. So that's the TRAPPIST-1 system, 7 worlds that could change everything we know about life in the universe. From the scorched inner planet TRAPPIST-1b to the frozen outer world TRAPPIST-1 from the potentially habitable TRAPPIST-1e to the mysterious water worlds of F and G. This system is a treasure trove of scientific wonders. I want to hear from you. Which TRAPPIST-1 planet fascinates you most? Do you think we'll find life there? What do you imagine life on a tidally locked world would be like? Drop your thoughts in the comments below. I read every single comment, and I love hearing your perspectives on these cosmic mysteries. If this video expanded your understanding of the universe and got you excited about the search for life beyond Earth, please hit that like button. It really helps this video reach more people who share our passion for space exploration. And if you haven't already, subscribe to this channel and click the notification bell so you don't miss future videos about exoplanets, space exploration, and the latest astronomical discoveries. Share this video with anyone who loves space, anyone who's ever wondered if we're alone in the universe, anyone who looks up at the night sky and feels that sense of wonder. Let's spread the excitement about these incredible discoveries to as many people as possible. The universe is vast, mysterious, and full of wonders we're only beginning to understand. The TRAPPIST-1 system is just one example of the incredible diversity of worlds out there waiting to be explored. As our technology advances and our knowledge grows, who knows what we'll discover next. Thank you so much for joining me on this journey to TRAPPIST-1. Keep looking up, keep asking questions, and keep exploring the cosmos with me. Until next time, this is Universal Information, reminding you that we live in a universe of infinite possibilities, and the next great discovery might be just around the corner. Clear skies, everyone.